Hey everybody, this is Mr. Ainsworth, and we're going to get into lesson 8 here on exponential functions. And this time, though, we're going to be talking about the most common example dealing with exponential growth, dealing with what's called bacteria. So I call this the bacteria example. All right, so check this out. Bacteria can multiply at an alarming rate when each bacteria splits into two new cells. All right, so again, you start off with one bacteria. All right, it splits into two new cells. Each one of those splits into two new cells, and then each one of those splits into two new cells. Every single time, each bacteria splits into two new cells. And what's going on here? I mean, how many bacteria are we gonna have at a certain time? So, for example, if we start off with only one bacteria, which can double, this is very important, which can double every hour, okay, of the day. At the end of the day, how many bacteria are there going to be? What do you predict? All right, so let's take a look at a prediction here. I want you to pause the video now and write a number down right here. All right, that's what I want you to do. At the end of a day, which obviously is 24 hours long, how many bacteria are there going to be if you start off with one and you double the amount every hour? Again, this is a doubling example. Go ahead and pause the video. Go ahead and write a number down there because you're going to be shocked. Okay. Okay. Now that you have written down a number there, let's go ahead and take a look at what's going to happen here. Now you start off in the beginning with one bacteria. It says if we start with only one bacteria, start with only one. Circle the word one. So in the beginning, we'll go ahead and at the start here, time equals 0 here. So start equals 0. You have one bacteria. At the end of the hour 1, you have two bacteria. At the next hour, at the end of the second hour, you have double that. So you're going to have to multiply times 2 here. 2 times 2 is obviously 4. That's where the doubling comes in, okay? So 2 times 2 is 4. You got to double that to get the number of bacteria at the end of the third hour. Now, you got to times it by 2. Well, 4 times 2 is 8. All right, you have 8 bacteria at the end of the third hour. At the end of the fourth hour, you got to double it. All right, 8 times 2 is 16. You got to double that to get the end of the fifth hour. So 2 times 16 is 32. And you got to keep on doubling every hour to figure out how many bacteria are present after the 24th hour. I love this example because this is a real example. This happens in real life with real bacteria. You'll see it in your science classes when you take a petri dish and put some bacteria in there and see what happens after a few hours. You'll have an unpleasant bacteria or petri dish because it's going to be filled with bacteria all over the place. Okay, you can't wait for you to try that in your science classes. Okay, so back here, we're at hour 5. Here we got 32 bacteria. It doesn't sound like much, but watch what happens. You're going to double that, all right, times it by 2 to get 64. Thank God you guys are familiar with these powers of 2 because we've been dealing with them so long. All right, you got to multiply that by 2 and you get the number of bacteria for after the 7th hour, which is 128. Now what's cool about your calculator is this. If you enter the number 2 in and you go times 2, enter, times 2, enter, times 2, enter, times 2, enter, you'll see the pattern. All these numbers are coming in. Times 2, enter, times 2, enter. It gives you the sequence of numbers here when you double or multiply by 2. We're at 128 bacteria after the 7th hour. But on the calculator, what's cool is that after you do it 3 times, all you have to do is hit the enter button and it doubles it for you because the calculator recognizes your your pattern of doubling. So after 128, well, guess what? It doubles, so you times it by 2 and you get 256. All right, look at your calculator here. Double it again, you get 512 after the 9th hour. So let's go ahead and fill the table in. All you have to do is keep hitting the enter button and it doubles your values. Okay, so after 512 you get 1024. Write small because these numbers grow very big. All right, after that we've got 2048. So 2 times 1024 is 2048. Like I said, write small. You double that and you get 4096. 4,096. You double that, you get 8,192. 8,192. After the 14th hour, you get double that, 16,384. 16,384. Now, you could keep on doing this and figure out the answer, at the end of a day, which is a 24-hour period. Okay, it says at the end of the day, okay, that's after 24 hours. Let's write that down. After 24 hours, how many bacteria do you predict there to be? Okay, well, you keep on doing this on the calculator and you can hit the button and you can get your answer pretty fast. But we're mathematicians here, and we want to use our skills, all right, of looking at patterns and predict the answer and use the calculator in a different fashion. All right, because what happens if I say what happens after 2 years? All right, you don't want to keep on pressing the button. You'll be there for a week. Okay? So what we do as mathematicians, we look at patterns. And we know from our previous discussions, all right, that 4, 8, 16, 32 are powers of 2. Let's write that down. These are all powers of 2. All right, 2 is 2 to the first, 4 is 2 to the second, 8 is 2 cubed, 16 is 2 to the fourth. We know this because we've had some experience here. We know that here you just take your 2 to the fourth and multiply by 2 and you get 2 to the fifth. 2 to the fourth times 2 is 2 to the fifth. You just add your exponents. You take 2 to the fifth times 2. Well, let me see. Actually, let me change that. There we go. 2 to the fifth times, 2 to the fifth times 2, well, that's 2 to the sixth. 2 to the fifth times 2 is 2 to the sixth. 2 to the sixth times 2 is 2 to the seventh. And guess what? That's 128. You're familiar with these because we've done these before. 256, well, that's 128 times 2, and that's 2 to the seventh times 2, which is 2 to the eighth. 2 to the eighth times 2, well, that's 2 to the ninth. There's a connection there. Let me see. After the ninth hour, it's 2 to the ninth bacteria. Let me back up. After the third hour, there's 2 to the third bacteria. After the fifth hour or fourth hour, there's 2 to the fourth bacteria. After the fifth hour, there's 2 to the fifth bacteria. After the sixth hour, there's 2 to the sixth bacteria. Out of the seventh hour, there's 2 to the seventh bacteria. Out of the eighth hour, or after the eighth hour, there's 2 to the eighth bacteria. After the ninth hour, there's 2 to the ninth bacteria. Well, guess what? There's a pattern there. After the 10th hour, there's 2 to the 10th bacteria, which that's 1,024. And if you don't believe me, no big deal. All right, let's check it out yourself. Let's take 2 to the ninth and see if we get 512. And on a calculator, that's super simple to do. 2 to the ninth is 512. Oh, holy cow, I'm right. 2 to the 10th, that's 1,024. So 2 to the 10th, 1,024. Holy cow, there's a connection there. All right, so after the 10th hour, there's 2 to the 10th bacteria. After the 11th hour, there's 2 to the 11th. After the 12th, it's 2 to the 12th. After the 13th hour, there's 2 to the 13th bacteria. Out of the after the 14th hour, there's 2 to the 14th bacteria, which is 16,384. Well, after the 24th hour, there should be 2 to the 24th bacteria. What's that? Well, let's figure that out. All right, so here we go. 2 to the 24th. If you write that number down, put the commas in, that's 16,777,216 bacteria. So let's write that number down here. Okay, so 16,777,000. All right, let's look at that number again. 216. So 216 bacteria. So at the end of 24 hours, there are 16,777,216 bacteria. Wow, guys. I mean, that's a lot of bacteria. And that's what we mean by something growing exponentially, because it increases so fast. I mean, can you believe that there's that many bacteria in just a 24-hour period when you just start with one and it just doubles? Can you imagine if it tripled every hour or quadrupled? Sometimes that happens too, depending on the bacteria. But I took a simple case of doubling. All right. Well, we know that in general, if there's X hours, what does that mean? Well, there's 2 to the X bacteria after X hours. and that's our function. So by looking at the pattern, look right here, by looking at the pattern, we can see that growth in this situation can be represented by the function y is equal to 2 to the x power. Again, after x hours, there's 2 to the x bacteria. Now, let's connect it with something I did before with money here. I said that any growth function can be represented by this. All right, this is a growth function that you saw in my previous lesson, where the base here is 1 plus r as opposed to the decay function, which is 1 minus r. Remember that a represents your initial amount, look right here. R is the growth rate, all right, as a decimal, and x is the number of intervals, and y is the number of bacteria after some number of time periods. Well, if the amount doubles, okay, the rate of increase is 100%. And you should know that 100% is 100 out of 100. R is equals 1. So here in this case, R equals 1. All right, now remember in this problem, we started with 1 bacteria. If we start, look right here, if we start with 1 bacteria, that means A equals 1. Let's write that down. A equals 1. And we can bring that down here. A equals 1, so Y equals 1 times the quantity, 1 plus R, but remember R, the growth rate, well, the growth rate is 100% because it doubles, right? You have twice as much. It doesn't grow by 50%, it doubles, so it grows by 100%, so R is 1. So let's substitute that in. And we're going to take it to the x power, where x stands for the number of time periods, okay, the number of hours in this case. In this case, let's put x equals number of hours, hours, all right, that occur. Let me write that better here. There we go. All right, what does this give you? Y equals, let me see, 1 times something doesn't change it. 1 plus 1 is 2. Holy cow, you get 2 to the x power. Let me change that. I was supposed to meant to say 2 to the x. All right, you don't need those parentheses. Just write down y equals 2 to the x. In general, the base is just being raised to the x power. Okay, so there we go. We've got that function there. We can go ahead and graph it and see what it looks like. We know what the function is, y equals 2 to the x. Let's go to the calculator here. Let's hit y equals. Put down 2 to the x power, this exponential function here. I think we better adjust the window, don't you think? Because if you look here, let's bring it over here, and you look at the table. So let's go up to the table here. Whoa, hang on. There we go. The table here, the y value is huge. It's 16 million. All right, 16 million. In fact, you know what? Let's just go up to, let's see here, 2, 4, 6, 8, 10. All right, so that's 1,000. Okay, no problem. So let's go up to 1,000. So we're going to obviously have to change our scale. So this is 2, 4, 6, 8, 10. Right there. This is 2. That's 4, 6, 8, 10. All right, we're going to have to go up to 1,000. Let's look at the values here. Let me increase or decrease the size of the screen so you can see this here. All right, so when here are the x values here. These are going to be x values. The output here are going to be the y values, these big bacteria numbers here. And after 10 hours, we got 1,024 bacteria. All right, so we're going to have to change the scale, obviously. So this right here is the number of bacteria. All right, and this is the number of hours here. X here, and this right here is going to be 2 to the x, or y equals 2 to the x. All right, so here we go. We're going to have to graph this. So at x equals 0, we get 1 bacteria. Now, but we got to scale the axis. So let me see. We're going to go count up to 1,000. Don't have 1,000 squares. So how about count by hundreds? So this is 100, 200, and so on. 300. Let me change the scale here. Or I mean, just zoom in so you can see this a little bit bigger. And then 400, 500. This is pretty easy to count. 600, 700, 800, 900, 1,000. Okay, you have to change the scale, people, when the numbers get big. That's one of those basic skills. Okay, change the scale. Okay, no big deal. All right, so let's go back up here and let's take a look at the numbers and let's approximate their positions on the plane. So at x equals 0, we got 1. So that's barely, I mean, if this is 100, then 1's barely above that x-axis there. I mean, I can't even plot it. It's so close. You know, 1 comma 2. 1 comma 2 is just right about there. 2 comma 4. So 2 comma 4. 3 comma 8. It's just a little bit above it. All right, it's so close to the line it's not even funny. 4 comma 16, we're getting a little bit bigger. 5 comma 32, getting a little bit bigger. All right, 6 comma 64, that's a little bit more than halfway. So it's right about there. 7 comma 128, we're over 100 now, so that's good. And then 8 comma 256, so 8 comma 256, right about there. 9 comma 512, that's getting a little bit easier to plot, over 500. Once again, you just have to estimate the positions here, and 10 comma 1024, that's over 1,000. So we're up, way up here. So look at this function here. No. Okay, you gotta put in the sound effects. All right, see these functions, or this function here, really takes off fast. These increase very fast because of the doubling. This is what we mean by exponential growth. It grows exponentially, which means it really takes off fast. For a small increase in x, the y values increase fast. This grows exponentially. That's what we mean, but when we say that, it grows super fast. All right, it grows exponentially. It grows super fast. In fact, let me write that down. Super fast, okay? Can you imagine what happens if it tripled every hour? Okay, and you'll see a computer-generated graph right here on the right. It takes off really fast. For a small little increase in x, it takes off fast. All right, go ahead and read right here. All right, this is what I meant. And let's, well, you can read this to yourself, but look right here. All right, this is what is meant by the expression increases exponentially. Man, for a small little increase in x, y increases exponentially. It takes off. It goes really, really fast, super fast. Okay, and this is happens all the time in science class when you deal with bacteria, or even in a rabbit problem here. Maybe we'll explore a rabbit problem later on. But when anything grows and either doubles or triples, we're talking about exponential growth here, big time. All right. All right. This is Mr. Ainsworth. Again, this is a video here. You can always replay it if you want. Watch or listen to any part of the video and repeat it if you like. And I'll see you in the next lesson. See you then.